Hello, my name is Bill Kinney. I'm a math professor at Bethel University in St. Paul, Minnesota, and this is part 16 of my video series about multivariable calculus using the computer program called Mathematica. What you see here is called a Mathematica notebook in which we can use Mathematica. We've been following along the second edition of Multivariable Calculus by John Rogoski, and we've basically gotten through the first couple sections of chapter 11 of that book. In this video, part 16, we're going to talk about polar coordinates. That's technically the topic for section 11.3. I still, as a unifying tool, want to put this in the context of my sub-series about calculations with parametric curves, so we're going to relate parametric curves and polar coordinates here. We've used the show and table commands in Mathematica before, but I'm going to use them in a new way at the very end of this video. It's very important to watch this one through all the way to the end so that you see the main point about polar coordinates when I use the show and table commands. Alright, so here's how I do things. I've got an example, and here's the example for this video. You can look this over and think about it, maybe pause the video. I'm going to go through the solution to that example, focusing on how to input the functions into Mathematica in a way that it allows me to use the other code to illustrate visually what's going on. And here you see the other code. The example itself is pretty easy to answer, I hope you see, if you've been following along so far. I also down further have an exercise that's similar, though maybe a little bit trickier than the example. And I'll show you the solution to that exercise written out down here as well. But then again, what's different about this video is at the very end, I want to put the example and the exercise together using the table and show commands to emphasize the main point about polar coordinates. Alright, so look at this example. It says, describe the family of parametric curves given by this function here. Theta is the parameter here. To this point, we've typically used t as the parameter because t represented time. Theta is suggestive of an angle, and in fact, this is an angle here. And this is suggestive of polar coordinates if you've used polar coordinates before. Theta is the parameter for this system of parametric equations, but we've got different values of r will generate different curves. So we really are thinking about what you might call the family of parametric curves, a bunch of different parametric curves, and we want to think about what happens as r increases. There's one parametric curve in the parameter theta for each of the infinitely many values of r greater than 0. Pause the video, think about it. Are you back? I hope you realize that this, for a fixed value of r, is going to generate a circle of radius r centered at the origin. And then to describe the family of parametric curves as r increases, you would just say that since r is the radius, the circle is going to get bigger and bigger. Its radius is r, it gets bigger and bigger. It's still centered at the origin, but the radius keeps getting bigger. We now want to focus on entering these functions in such a way that we can use the rest of this code here to illustrate this visually. This is code I've used before, though modified. I'm going to enter the functions initially as I've done in the past, though you should realize if you've got Mathematica open that I'm not going to leave these functions this way. I'm going to change them before I actually enter them. But just to remind you of how I've entered these functions before, I will type them as I've done before. Notice the square brackets. Variables for functions go inside square brackets. Also notice the underscores that are initially used when you first define the function. You can see that they are on the left sides of each of these equations. It is necessary to use that underscore when you first define the function. However, once you've done that, you don't use an underscore anymore. You can see I don't have an underscore here or here. I also don't have underscores inside the cosine and sine. Notice the cosine and sine are capitalized. That's important. The colon equals is technically not necessary, but I like doing it. The semicolons separate the different lines of code. Actually, to suppress output. It's not really necessary here, but I like to do it. Alright, so this would be how I'd enter these functions in the past. However, I am interested in seeing the circles increase in radius as r changes to see the full family of parametric curves. And the way I'm going to deal with that is I'm going to actually use the basic math assistant over here and press this subscript button to make a subscript, and the subscript is going to be an r. And Mathematica needs to know that when it makes the animation, it needs to treat r essentially as a variable as well, so I put an underscore after that r as well. To save some time, I'll copy and paste and then modify. I do that for each of these functions. I also need to put underscores for these things, but with subscripts, but without underscores for the r's. Alright, this would be fine. This would be a fine way to enter these functions. I'm going to do one more It's a kind of strange thing that in general is not necessary for the situation, but will help me show you the relationship to polar coordinates at the very end. I'm going to emphasize that these are functions of theta by putting an extra theta up here. This is not necessary, and in doing so I've really changed the names of these functions. This one has become f theta instead of just f. I'm going to put that there, here, 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 and here. That's how I want to enter these functions. For the exercise further down, I'm going to put an r instead of a theta. In fact, I've already typed it in. All right? So that emphasizes these are functions of theta. I also like making a habit of creating two other functions here, the speed and the distance traveled. The speed is an instantaneous speed at time t, or in this case at angle theta. And in this case, the speed is constant. It's actually the constant r. Think about that. Hopefully you recall from watching previous videos, or you just know this, that in this kind of situation with a parametric curve like this, that you find the speed by taking the square root of the sum of the squares of f and g, of the derivatives of f and g. In other words, the square root of f prime of theta squared plus g prime of theta squared. Take a moment to do that. Pause the video. Use the fact that cos squared theta plus sine squared theta equals 1. If you simplify and use the fact that r is positive, you will see that the speed really is equal to r, which is really a constant for us here. How about the distance traveled? Dist sub r here of theta. That's an antiderivative of the speed. Speed is a constant. We're anti-differentiating it with respect to theta. You get r times theta plus c, but we want to take the c to be 0 here because we want distance traveled at theta equals 0 to evaluate to 0. So r times theta will be the right formula for the distance traveled. Let me also put an extra theta after these function names here and here. Now I can enter these by doing shift return, and I've got it set up in such a way that I can now enter the rest of the code here. You might want to pause it and look it over. Again, you don't have to understand this code if you don't want to. Ultimately, we are going to now animate this all with manipulate. All right, and see all these graphs together in one picture. These are my animation sliders here. B is really theta as theta increases. I can play this. Watch. You see a circle get traced out as b goes from 0 to 2 pi. I actually made these graphs probably too big here. I'll leave it. That's okay. So here you see a circle of radius 1 centered at the origin. R has a value of 1 here, but now watch as I increase r, the circle gets bigger and bigger. R is the radius of that circle. You also see some other graphs. This is y as a function of time. That's r times sine theta. It's a function of theta. This graph down here in the lower left, it'd be nice if I could make that graph bigger, but it doesn't work real nice if I do. That's keeping track, look at it sideways, of x as a function of time. It equals r cos theta. Over here in the lower right is the distance traveled and speed functions. The speed function equals r. It's a constant. You can see as the value of r changes, that horizontal line goes up and down. And the distance traveled has slope equal to r. Its formula again is r times theta. All right, that's the basics of the content of that example. Now let's go down and look at the exercise. And then we'll put everything together like promised at the very end to talk about polar coordinates. Here's your exercise. Pause the video. Think about it. I hope you realize that it's going to generate a ray emanating from the origin as r increases. And as the value of theta increases, this ray has an angle that changes. So here's my solution down here. You can pause it and look this over. And then we will animate it further on down. Enter these functions, enter this code, and we will see as r increases, the ray is generated emanating from the origin, and as theta increases, we go around. Different values of theta give you different rays. Although, if theta increases by a multiple of 2 pi, you get the same ray. Alright, now we want to put it all together. Show, first of all, is a command that combines graphic objects into one picture. table is a command that generates lists of things, and so what I'm going to generate here with table is I'm going to generate a list of plots, a bunch of different plots, and then show is going to combine those plots. What plots am I going to make? I'm going to go back up here. Remember I said paraplot generates the parametric curve. Paraplot theta generates the circles. Its inputs, going back up here again, are R and really these are theta. The B is really theta up there. R and B values where B really represents theta. I'm going to let B equal 2 pi to generate the entire circle. And then R is going to be the radius of these different circles. It's going to start at a value of 1 and let's say go up to 20. When R takes on these different values, I get different circles. So again, paraplot will plot the circles. Making R go from 1 to 20 makes it plot a bunch of different circles. Table puts those graphs together in one list, and then show combines all the graphs together in one picture. And here's what I get. You can see I got a bunch of different circles of different radii centered at the origin. I can also do that with the paraplot R right here to generate a bunch of different rays. Do something similar. I'll do a copy and paste here. Put a comma between these. Change the theta here to an R. Up here it's the theta that's changing. Change this R to a theta. And the B now represents R now. If I just go out to say 20, that'll be good enough. Theta is now going to increase from 0 to 2 pi. Not in units of 1, but in units of, say, pi over 6. That'll generate a bunch of different rays. There we go. Maybe I should do pi over 12 instead of pi over 6 to make more of them. Alright, a bunch of different rays. Pi over 12 units apart, which would be 15 degrees apart. Let's see, 15, 30, 45, 60, 75, 90 degrees. Yeah, this looks correct. And what we have here to make the final point is that this is a polar coordinate grid. Each point in the plane has polar coordinates given by the r and theta values where the point happens to be. Where do these circles and rays intersect? For example, this one right here, that looks like it is along the circle of radius 11 and an angle of pi over 4. Its polar coordinates would be representing the r and theta values. They would be 11 comma pi over 4. Another example, say we take this point right here. In rectangular coordinates, xy, that's the point 0, 5. However, in polar coordinates, the radius of the circle is 5, and the angle here is pi over 2. Its polar coordinates would be 5 comma pi over 2. I know I said that quickly because we're out of time. In the next video, we'll get into more depth about polar coordinates more specifically.